The others, what do you know about graph? Okay. Okay, everyone. So now let's start with graph theory. Okay, I will show you yeah, the basic notion of graph theory, and then we try to go into algorithms and then complex algorithms and its application. Okay, so idea for this graph theory. This is a slide I take from my professors for my master degree, but it's a list that I will show you what can we do with graph and how we can formally define a graph that may help you in some like research projects later in the future. Okay. Now we start with this one. So we have few chapters, and it depends on the time and the progress. We try to go through all of them if possible. Now, at the beginning, we try to show you some notion that could be scary at the beginning, but that could be the thing. So we have some notion here. So if for natural number, real number positive only, star means without zero. So there is some notion, and normally function people will write like this. This is function f that take an input from the natural number. It's been integer natural number and return a number in a real number different from zero. That is the that is just definition. Okay, and in maths or in graph theory, people use a lot of this kind of formula. Okay, this is quite scary at the beginning, but I will try to show you some of them. Okay. Now, this actually is the definition of the complexities for the algorithm. Okay, we will not go into detail, so just show you the difference, some different notion. Now we skip these parts. Now we go to graph. In graph theory, we have many kind of graphs. In graph that have no direction, we have undirected graph. If we have direction, we call it directed graph. And here there's some basics, notion that we should remember. People can define a graph just a tuple. Graph is a combination of x and u, while x is a set of vertices, u is a set of arcs or edges. You can use any name as you want. Okay, here u, x, and u. Here is a function. What we say, t is a function that take a u, which means an x, and return a vertex. So it means that t, you give it an edge, and then we return you a vertex. And here we call t a terminal extremity, means that if we have a graph from A, let's say I will try to draw try to draw it in pen. Why not? Okay, let's say if I have a graph, I would say I have this one go to this one in direction. Okay, so here the graph, so we say we can name it A here, whatever you say, the name E, and we have graph G. Here is a set of a tuple of the combination of, we have two vertex A and B, no, only two of them. Here a set, and the set of edges, in this case we have just one edge, say A, B. And people say, if you have a graph with direction from A to B like that, so we call it this is the terminal. Đây the key, terminal, extremity, and I is initial extremity of the edge AB. That's it. But they define it formally like this one. T is a function. When you give it an edge, that will return you a vertex that corresponding to the terminal extremity of that edge. If I is a function, it takes an edge and return it to you a vertex that is the initial extremities. Okay, so we say if A in edge belong to the set of available edges of the graph G here, so we say A x, y, it's direction here, the vector, say where x and y are extremity of A. So that's it. Okay, so that is just a notion. We can say that if we have an edge from x to y, so x to y belong to u is within an edge, then we can say that x is the predecessor of y and y is successor of x. Here, A is a predecessor of B, B is successor of A. Okay? The notion. Now, what people say, now if we have a matrix like that, if we have a graph like that, the question is how can we define or represent a graph in our memory? Because we cannot draw it in a screen and put it to the program, put it to your Java code or Python or whatever you have. So what they have to do is they have to represent it somehow. And the way to represent it, we'll show you 2 or 3 ways. The first one, we call it adjacency matrix. Okay. They say if the graph G defined like that, a direct graph, it means we have direction. We have here, the notion is the number of items in the set X, n. It means we have n vertices and we have m edges. Okay. So the set of vertices, we name it we label it from 1 to n. The adjacency matrix is a square matrix, n by n, where each position Aij is have the meaning that here we have the value. This is the number of arcs with the initial vertex equal to I and final vertex or terminal vertex equal to j. So we say this is the matrix. Okay, here let's say we have here 0 for 1 1 means there is no edge from 1 to 1. Here, this number 1, we have 1 edge from 1 to 2. 1 to 2. Here we have 1 edge from 1 to 3. 0 means we have no edge from 1 to 4. That is the adjacency matrix. Okay, so here we have what? 2, 1. We have 1 edge from 2 to 1. So we have 2, 2, nothing, nothing. So we have 2, 3, nothing, 2, 3, nothing. 2, 4, nothing. 3, we have 3, 3, 1, nothing. 3, 2, 3, 2, 1. This is 3, 3, nothing. Yeah. 3, 4, 1. Okay, 3, 4. Okay. And the same go for 4. There's only 1 edge from 4 to 4, and that's it. Okay, everyone. So that is the first thing. So how we represent a graph in memory. Now I will show you one sample graph, and your task is to draw the adjacency to define the adjacency matrix for that. Okay. Say what can we do it? How can I do it there? Okay. Now everyone, so based on this definition, now please try to draw the build the adjacency matrix for this graph. Everyone, please do it. Mm-hmm. The others, please try. Okay. A to B, B to E, A to B, okay. B to C, B to E, B to F, C, E, F, okay. C to 1, C to D, C to G. Okay. Yep. So most of you here submit the work here is correct. Đạt, Hà Tiến Đạt, why you have the edge from B to A, no? Why? Đạt, I think you put the column and row in the wrong order, no? Hello Đạt, Hà Tiến Đạt. Do you see that you put the column and the row in the wrong order? It means if we have this one, that number should be in here. Say with read A, there's an edge from A to B, so I should have the value here, 1 here, not over there. Okay? Okay, Đạt. Okay. So everyone else, do you have a question on that? This is quite easy at the beginning. Okay. So continue. So what we have is now we move to another kind of representation of the data. So we try to do is we have data for Reup, but we show it using, we call it incident matrix, which means that we put 1 for the initial of the vertex of an edge, minus 1 for the final vertex of an edge. Okay, so here the matrix is not a square matrix anymore. That will be the m. It's been a number of vertex here, and multiplied by the number of edges. Okay, that will be like this one. So for a same graph, we say for the first column that represents the first edge, the initial vertex is A1 here. So not vertex number 3. So we will put 1 at 3. So for a terminal vertex, we put it minus 1. Okay. So we have here input, initial and final or terminal. The second edge from 1 to 3 to A2. So initial is 1, terminal is 3, and so on. The last one, there is a special thing where we have form around 4. This cannot represent in the incident matrix. Say we cannot say anything about 4 go to 4. Okay, but at least they show that they have a cell loop matrix, cell loop edges. Okay, that is the thing. Now then we can compare the memory usage between the adjacency matrix and the incident matrix. In this case, you see that if we have the graph that just have few edges, then the incident matrix can save us some memory because it's not m by n squared for all situations, but depend on the number of edges. Okay. And here we always have the fixed number of size for the matrix. We call it adjacency matrix. Okay. Now move to the next one. They have a second kind of graph. We call it undirected graph. Undirected graph means we have graph what we have no direction. Okay, so here, so we say x and e, and we have 1, 2, 3, 4, 5. It's just vertices, and edge just here. This means they can have no directions. People can go from 1 to 2 and 2 back to 1. They may have parallel edges. For some reason, I don't know why, but you can have 2 parallel edges from 1 to 1, 1 to 2, 2 times. Okay. And in this case, just we have undirected graph with that. Another notional graph. So people say that if we have graph, we can say sample graph. Sample graph means they have no loop and neither multiple edges. Actually, that would be very important for many algorithms, because if we have loop and we have multiple edges, that can cause some problem for the algorithm in the futures. So people call this type graph is sample graph. Okay, and we can always define the adjacency matrix and incident matrix for a graph. So adjacency matrix is just like the other one. A1, Aij will be the link from I to G to J. Yeah, if we have incident matrix, so the value in the incident matrix is the number of times that we have I link to that edge in the graph. Okay, so here we have some example. Maybe here for incident matrix we say 1 to 2, so 1 linked to E2 here. If we have see here 2 linked to E2 linked to E7, so we have 1 for 2 here, 1 for 4, both of them, because they have no direction. And this say that if we have loop, so we can use value 2. Before we cannot use any value because it -1 and 1. Now we just have positive number. We can use 2 for the loop in incident matrix. Okay. Now we have some other notion. So we say two vertex x and y in the directed graph or undirected graph are adjacent, just the name. If they have an edge in that graph that link x and y together, it could be any direction, so we call it adjacent. Incidence, these come from the notion of incident matrix. Is the edge incident of an edge if we have an edge contain x in that part, x or y. Okay. Now this is the notion that we really want to say. First of all, the neighborhood of a vertex, it's mean all the neighbor. So they the notion. Here how we read the formula. The neighborhood of a vertex x equal to a set. Okay, this is a set of y belong to x is a set of vertices. Okay, where there exists an edge x, y in the set of edges of the graph. Okay, so neighborhood is mean on the adjacency adjacent vertex of a given vertex. This one, another notion, say the degree of a vertex. So a decrease of vertex just say is the number of neighbors. That's it. Okay. So we have a vertex x. We have 10 neighbors. The degree is 10. A bit more detail in direct graph. people can say about outgoing degree and in degree. So it means we take care about the number of h that we can reach from x. So we have the direction x to y. So here the outgoing edges, outgoing neighbor. So we have minus. So we have all of the vertex that can go to x. We say minus. So in neighbor. So we call it out degree and in degree. Okay, now time to just count. Here, just do some calculation. Okay, make it bigger. Up. Sorry, I cannot do it. Up, zoom. Can I zoom? Okay. So now, please tell me. Try to compute the. Something wrong with this. Let's see. Okay. So now try to compute the in and out. So here, so for A1, so we have the degree of A in general, that will be 2. Okay, so our degree is 1 because you have only on one our in H. So you have in degree is 1. Okay. So B, what we have our degree is 1, 2, 3. In degree is 1. So here we have what? E, our degree 2, in degree 1. So actually people can base on in and out degree to say something. First of all, what does it mean if we have a vertex that whose out degree is 0? What does it mean by that? If our degree is 0, we can say that our degree is 0 mean, yeah, we cannot go anywhere. Okay, go to any other vertices. Okay, if we have the opposite, if we have in degree 0, means that no one can reach that node. Okay, so just by using this degree, people can summarize the status of the graph. Okay, so one application is we can represent the friendship in Facebook, let's say. So if we have friends, we have one edge from you to your friend and one edge back from your friend to you. It is two edges. We have one direction. Say if I just follow you, I'm not your friend, I just follow you, so it is one direction. Okay, now based on that, people can find out who are the let's say the key influencer in the social networks by checking on the number of in degree. Okay, so see how many followers they can have. Or in the school, in the context of the school, we may analyze the relationship between courses in our IU. So we check whether or not we have some course that are very, very important This means it is the prerequisite of many other courses. So we represent it in graph and we just count the in degree and out degree of the node. So we see the thing. Okay. That is in and out degree. So there is something. People say that the proposition is been. People can prove that in the simple unoriented graph without loop and multi edges, we can say m is number of edges is always smaller or equal to this number. It's been number of any number of vertices, any number of vertices. So what does it mean? Means that for a graph, undirected graph, we can know what will be the maximum number of edges we can have for the graph. Means at most every pair of graph, every pair of vertices in a graph we have one edge. So that is the max. Okay. And here what they say, for any the sum of all of the degree in and out, because they undirected, degree of a graph of a vertex, and the sum of all of them will be 2 times of m. That's quite trivial because it is undirected. For one edge we carry 2 times, one for the initial, or it's one for one extreme and one for the other extreme. So we have the number of degree here is 2 times of number of edges. Okay. And that is the thing. Now people, think about this one. If we want to say the proposition is merely true, the number of vertices have an odd degree is even. First of all, do you think that makes sense? Hello. Hello, hello. Okay. Think about that. If you really want to play with the theory like that, so at home try to prove that this is true. Okay. Otherwise, just accept that. Okay. So now they have another thing. For dialectic graph, the decrease in number of in and out. This one. Here the decrease is number of neighbors. Say here in this graph. Yeah. So we have the graph and the decrease of A2 Degree of B is 1, 2, 3, 4. This 1, 2, 3, 4. 1, 2, 3, 4. See here? Let's say this one, the degree is 3. And they say that in the graph, they have the number of vertices that have odd degrees is even. What's it? Sorry. So check. This means we have here one vertex that have our decrease here. The decrease is 3. And they say that in the graph they must have another one, at least. I'll try to prove it. Okay. So in this case, that is 1, 2, 3. Okay. That is the proposition. And now for the dialectic graph, what we know is that the number of in decrease and number of out decrease of on the vertices in the graph equal to the number of edges. That's quite straightforward. Okay, and now we move to another thing, that is, they say that the way that to represent data, say adjacency matrix, incident matrix in not dynamic, it means statics. Means that if you want to add or remove the data, let's say if you want to add one node to the graph, that will change. It means you have to modify the matrix. It's by adding one new column or two, or one column in one row, depending on the type of structure you have. Here, if you want to have a dynamic structure, so the linked list, okay? So the linked list is like this one. So they call it a list of successors. Actually, it's the way that people will use for a graph. That save a lot of time and memory. Say if we have 1, 2, 3, 4, 5 edges, so we define a list, an array, or a linked list if you want, of 5 elements, and each element here will be a linked list of the list of successor of 1. Here is the row here is not about the edges in the graph, but just the linked list. They say for 1 here, 1 have 2 successors, 2 and 3. So in the linked list of 1, we have 2 and 3. Okay. So 2 have 1 successor only. So we have 2 linked to 3. This one. And 3 have 2 successors, 4 and 5. So we put it like this. Okay, everyone? Is it clear? And again, just try to do it here. Just use a list of successor to build this one. I don't know how to make it bigger. It's a min. Okay, again, everyone, please draw the list of successor for this graph. This one, yeah, say you not bad if you want. You can always say here, from 1 we have linked list is 1 and 2. Let's say 2 and 3. Hey, linked list, let's say. And 2 have link from to 4. That is linked list. Say, if you want to say, I don't know what. So back to this one. The others. The other, please submit your work, please. Hoàng Minh, we will not, if we are the successor list, we don't have to repeat B again. Let's say for the first row, that will be A, the list store only B, and for B, the store E, and E will point to F, F point to C. That will be the thing. Okay. Yeah. No, for the second line, we Hoàng Minh, we don't have this one. D, we just have E, B column, and then E, F, C. It means it's just a list of successors without repeating the first characters. Okay, Phạm Hoàng Minh is okay. Everyone else, hello. Is it okay for you? So now I'll move on. Now we have a graph, how to definition of graph, and then we have a basic notion how to represent it in a memory. Okay. Now what we want to say we want to use a function to go through let's been traverse or explore the graph. So we have few notion. Say it's a work. A work is just a circle of vertex next to each other. X1, 2 is K. In such a way that for every pair in this list, they must exist an edge in the graph. So you can say it's just a list of vertex, but it's not a random list. Here, the link that you go from one place to another. They say a work is closed if the starting vertex equal to the ending vertex. Okay? This is a work, and the path is a work without repetition of edges. So for each edge, we use only one. Say here we have the path, the work. Say A, B, E, A, B, F. That is a valid work. And it's closed if we have A, B, E, and A again. So it's closed. The starting and the ending vertex is the same. And the path, they say the path is a path is a work without repetition of edges. Means that we say A, B, E, and A. That's it. We cannot check A, B again because we checked that edge already. Okay. A circle is the closed path. It means we don't have any repetition of edges, but the starting vertex and the ending vertex are the same. And here, the last notion would be elementary path is the path without repetition of vertices. For circle, they have one loop. Means that, say, if I have A, B, and from B I go to F, From F, I go to G. G, I go back to F. That is not elementary part because we repeat this one, F. Okay. So what we say, elementary part is when we take an edge, every edge only once at most, or every vertex only once at most. So here, please everyone, in this graph, give me a okay, I will show you first maybe. Here, here there is a work from A, B, C, E, then B, D, D, so then B, A again, whatever you want. But we don't want to repeat the edges, so we have A, B, D, E, and B, C if you want. Okay, elementary parts, so we don't want to repeat edges and vertices, so say A, C, E, F. That's it. Okay. Now, for this one, try to give me some list some first of all the part is mean without repetition of edges. Just pick one of them. Now the next question is this, like the one of the game you have at your childhood. So say, show me a path that go through all vertices in the graph. So everyone, please. Hello, hello. Hello, please. everyone. If show a path, and path through everyone, are you there? Hello, are you there? Someone? Okay, I'm sorry. So here, for this graph, actually they have many paths that go through all the vertices. No, you can say your friend say A something, but you can start from A. Is it possible? Say A, go to B go to E go to F go to G go to oh sorry, it's not the good one. So we have to go back from what? Can we go from here? No. This one, and this one. Say okay. Let's start from E. Yep. E A B, and then we go to C go to D go to H go to G and F. Okay. Yeah. So that is what we try to do. But now we are doing things in manually. Okay. So people. So we try to do say. We do it manually. Now people would try to apply some algorithms to find out the thing. Okay. So that would be the Reup theory application. Here we try to go some other properties before we go into the algorithms. So here for direct Reup, Reup or the direct graph, for x and y belong to V is mean set of vertices. The distance between x and y is the number of edges of the shortest path linking linking x and y. Okay. So the shortest path means we don't have repetition of edges. Shortest path will be the distance. Okay. Okay. So we have a notion of distance in directed graph or graph in general. So for the now, let's have a small break, and then we'll try to read these algorithms, BFS. But here we use a code to implement the algorithms. Okay, let's have let's say few minutes, 10 minutes or so, or 10 minutes of break. Okay. Okay, hello everyone, welcome back. Now that we go to the important section on the algorithms to have us to explore a graph. Okay. This one, I'll try to text. Let's say okay. Now, we want to implement the breadth first search algorithms. Okay, so that is the algorithm have us to explore all of the the vertices in a graph. Okay. Okay. Now, I assume that you have nothing about BFS and then, so I will try to. Okay. Okay. Now I. Okay. Now, let's have a look at the algorithms. So what we say, we have preferred search. The idea is, say we have a graph, and for the searching, we must somehow say give us a starting point. It's mean the first vertex that can we can explore. Okay. So now at the beginning, we have the data BFS. Now the BFS algorithms, they explore the graph, but in the same time, the BFS algorithm can help us to do many other tasks. So in this case, the algorithms try to store many information as possible that we can use it for the other task. Okay. First of all, we have few notion. This is color. The color is just to mark the status of the vertex, whether or not it's new, is when we never reached that one. Sorry. The status, we have white, it means it's new, we never reached that not before. Gray, this is the color. Gray means we are working on that. Okay. And black, it means we're done with that. Okay. Now we have the second value D, named for distance. We try to measure the distance from the source node S here to a given node. At the beginning, we say for each vertex except S, we set white, the color is white, the distance is infinity, and here the pi means the parent of that node. That is mean we try to track how we can reach a given node or given vertex. So we put it none, it's mean empty, nothing. So at the beginning, we start with everyone is white, infinity and none, and we start with the color S of S, the source to gray. Let's say in this graph, I try to do what? I try to okay. Okay. So let's say I try to pick A at the starting node. Okay. So at the beginning, we have two things. So color, we put it gray. Let's say I mark it gray like that. I'm working on this. Okay. And the distance from S to S is 0. So we have 0. So have the parent of S have nothing. Okay. And we have F is a Q. So what we say at the beginning, we have the Q. Say the Q like that. Okay. We put S into the Q. S. What we will do is, if the Q is not empty, we try to DQ, so we get S. Okay. And then we, for each adjacent vertices of U, in this case S, and we put, if the adjacent matrix, adjacent vertex is white, then we put it gray. Let's say here A, the adjacent of A is B. Okay, B is white, we put the color red. Okay, and we say the distance from the source to V, that means B in this case, is the distance from the source plus 1. So the distance here will be 1. Okay. The parent of that node will be U. You indicate S. So the parent of B, we say A. Okay. Then we go to the next adjacent of A. In this case, nothing except B. We just have one adjacent node. So we mark A is complete black. So it's a lot. Let's say black. I will put it here to mark it black. Okay. So we finish with A. Now here we have one step I forget. So we put B here in the Q. So we remove S already. Now we do the while loop again. So the while loop start with B. We take out B. So we DQ B. We check all the neighbor B. In this case, we have C, F, and E. Okay. We do first with C. C white. We put it gray. Okay. And then the distance of C will be 2. It's been 1 plus 1. And the parent of C, B. Okay. And we put C in the Q. Then we have BF. We mark F is this one. The distance is 1 plus 1 is 2. And the parent of F is B. Okay, put F here. Last one, E. And to B. Okay, and put E here. The Z for B, so we mark it finished. Get black. Okay. Now continue. We get out from the Q, we have C. See here. We have two exaction of C, D, and G. So D right here. The distance with 2 plus 1 is 3. And C. Okay. And put D here. And this one again. So we have 3 and C. Okay. So it's done for C. Remove it. Okay. We put G here. Sorry. Okay, we go back to the Q. We have F. F. We DQ everything from a neighbor of F. Neighbor of F is G. But G is not white anymore. So we do nothing. We finish with F. Okay. E is the neighbor of is A and F. They are not white anymore. So we don't do E. Okay. So we have D. D. Neighbor H. Okay. H. So we have 4 and D. Put it here. Okay. Then we finish with D. So G. Neighbor of G is F and H. No, all of them are not white. We finish with G. And then with H, nothing left. So we have notes done. That is the BFS. And if we are working on this, we have something like this one. We see that from A, we go to this color is not good. So this one. From A, we go to B. And B, we do go to this one. Okay. And this one, this C, we go to D using this H. And C, we go to G. And from D, we go to H. So as if you want to break it into level, you see this is level 0. I will use another color. This level 0. And this up. What? This 0. And this level 1. Yeah, 1. And level 2. And level 3. They say that the BFS actually would have us to go through the projects to the Reup level by level. And after we finish the BFS with this one, what we have is we have the distance from every node to the source. So we have 4H. It's been from A, we can go to H with 4 steps. And to find the link, we say here from H go to D, and D go to C, C go to B, and B go to A. Okay. See, after running the algorithms, that's what we have. So, is it clear for you, the algorithms? Everyone? Please try to run the BFS algorithm on this graph, starting from A. Everyone, please. Mm-hmm. Yeah, that. So you have 0 here, let's say. So from A, we take part to C, okay? So we have 1 here. So from C, from A we have H, okay? This is level 1. From C, we go to C, go to D, it's level 2. From that's it. From H we go to G and F. Okay, that will be number 2. This is number 2. Okay, and then from D go to F, but F visited, we don't touch it. So from H we go to this one, so I have number 3 over there. So from G we go to this one, so we have number 3 over there. A, C, H, D, G, F. Okay. Then we have I and J. Everyone, do you have the same solution? So have level 0 here, level 2 over what? Level 1 is here. Level 2 is here. Okay. And the last one will be level 3. There's something special about this graph. That's it. We have few nodes that are not reachable. The others, do you have the same result? Hello, hello, hello. Everyone, question? Okay. So that is BFS. There one remark. First of all, the BFS algorithms here, you see that have many other attributes other than just the path. And in a graph, it's not always the case that we can reach all of the vertices in the graph starting from one point. Okay, because you see here, from B they have no link that is the in degree of B is 0. Or in degree of E 0, for sure we cannot reach it. Okay. Now some remark on this one. First of all, for the complexities, of the algorithms, so at the beginning all of them are white, and then discover and become gray, and the vertices are visited become black. So they have three notions. First of all, the number of vertices is n, number of edges is n. So from like 1 to 4 is when we set up the initial value. We check it n step. From slide 12 here. So we go through all of the we will do the while loop, and we visit all of the neighbors of the node. In the while loop is done almost at most it means the number of edges. So the complexities of the algorithms is that m plus n. It's been n step. Okay, and we have this one in the graph. The tree that we have here. Oh, sorry, I put many things. This one is the tree I draw from this one. From C we go to D. From D we go to H. This one. From C we go to G. So the graph, or the tree actually a graph, from A to B using just the blue, the cyan edges here. We call it the spanning tree. Spanning trees mean the tree that go through all of the reachable node from the starting node. We call it the spanning tree. Okay, and that will be the tree of the shortest path. It means this is the path, the shortest path from A to every node that reachable from A, like that one. Here is the shortest path. Okay, that is the role of BFS. It means we can use BFS to find the shortest path in the graph. Okay. Yeah. So here they say if we have the if we want to compute the distance between S vertex of G, then we can just use the BFS to compute an on determination on the vertex V has value. It means if it's not infinitive, it means the BFS can have us to find out the shortest path, and that will be the path that we want to find. There is some lemma here. I will skip it for a moment, but here the last one. Say if we have the graph, directed or undirected graph, assume that BFS is run on G, start with a given source S. Then after execution, they will try to discover on a V that reachable from the source S, and on the termination, the vertex D will be the shortest path from S to V. Okay, from the source to V, that's what we want, what we have. Okay, and there is one of the shortest paths, only one of them. We may have many paths that can reach a given node, but this is one of them. Okay, so that is for the BFS. Oh, that's it for this section. Okay, so next time we will learn about DFS, and the application of DFS is a bit more complex than BFS, but for a moment, that's it. So do you have any other question? To sum up, what we learned is we learned few notion on graph, the way that we can represent graph in the memory, and then how to run one of the algorithms, say PFS on the graph. Any question? Hello. If no, that's it. Then see you next week. Okay. And now just one more thing. I really want to have some makeup section, and how we can organize it. Do you have any available slot for whole class? Is it possible for you to use the lab section, because last week we have the lab section on Monday afternoon? Are you all available? So please like the message to let me know how many of you are available on the Monday afternoon. Okay, for a makeup section. It's been I will use a lab for makeup. Okay. If Monday afternoon is not suitable, please tell me. Try to make a pool or something. From Monday to Friday, try to find a day. Sorry, Tuesday afternoon I have class. Okay, otherwise try to discuss Tuesday afternoon not available, so try to have another day. Okay, otherwise see you, bye.